A radiopharmaceutical is a chemical compound tagged with a radionuclide administered to a patient for a specific diagnostic purpose. For diagnostic use, they are administered in tracer quantities and delivered to specific target organs. The ideal radionuclide should firstly deliver as low a dose as possible to the patient. Secondly, should have a short half-life appropriate to the organ being imaged. And thirdly, emit a monochromatic energy source of between 100 and 300 keV. This is the so-called Goldilocks zone, where the energy of the nuclide leaves the body easily and is at the just right strength to be detected by the scintillation camera without overwhelming it. Technetium-99 is a good example of an ideal radionuclide. It emits very little patient dose while being easily detected. The ideal chemical should firstly be non-toxic, secondly be suited to uptake in a particular organ, and thirdly, the chemical uptake should be substantially different between normal and pathological conditions. The greater the difference between these two ratios, the better the contrast for imaging the disease. To label a particular chemical with a radionuclide, a known activity of sodium pertechnetate is introduced into a kit vial, mixed together, and after a few minutes is ready for use. As commercial nuclear pharmacies may be located several hours distant, most labeling is performed at the infusion site. Labeling is performed in order to ensure that the radionuclide has attached itself to the biochemical. In this case, that the technetium has attached to the molecules in the kit. After shooting and shaking, there will be two types of impurities remaining. Firstly, free pertechnetate, which is not reduced, and secondly, hydrolyzed technetium, which is reduced but not tagged. When the sample is removed from the vial and placed on the test strip, the bound pertechnetate stays put and the free pertechnetate then moves up the strip. We measure the difference between the labeled material and the free pertechnetate. This is expressed as a ratio, and all that is needed is for the sample to fall within the acceptable range provided by the manufacturer. Remove the test strip from the container by sliding the lid. Draw a pencil line 1 to 1.5 centimeters from the base of the strip. Using a tuberculin syringe, place a single drop at the level of the pencil mark. Place the strip in the solvent tray with the base of the strip touching the solvent. Observe the solvent moving past the origin point by about 2 centimeters. Open the glass door slowly and remove the strip. Mark the advance of the solvent with a red pencil. While securing the strip with your finger, dry the strip of the solvent with compressed air for several seconds. Place the strip with the origin over the well counter hole. The detection time takes 6 seconds to count. Move the strip so that the solvent front is over the hole, then record the value of the sample in this position. Once the labeling efficiency of the kit is determined, discard the test strip in the hot trash. Testing for sulfur collated labeling efficiency requires thin layer chromatography as well as pH testing. Place 1 drop of the solution on the chromatography paper and 1 drop on the pH test paper. As sulfur collated is very concentrated, the smaller the drop placed, the better. Hold the pH test paper in front of the pH color chart and ensure that the color is in the range expressed on the chart. Chromatography for the sulfur collated solution is tested using a 85% methanol solution. The strip is placed in the solvent tray and time allowed for the methanol to climb the test strip. After about 7 minutes, remove the test strip from the test tray and dry with compressed air. Once again, place the origin over the well counter aperture. Clear the reading on the computer and observe the value. Move the test strip so that the solvent front is over the aperture of the well counter. Reset the counter and observe the value. Subtract the value of the impurities from 100%. Discard the syringe, pH paper, and test strip in the hot trash. Radiochemical purity is determined for each vial prepared. The limit for purity is derived from the USP monograph, the package insert, or as specified by the nuclear pharmacist. The MAA test requires both a labeling efficiency test using the MEK solvent as well as testing the particulate size. Place a drop in the center of the hemocytometer slide. Cover the droplet with a cover slide. Examine the sample to observe the size of the particles. Each reference grid is 50 microns square. For this example, the acceptable limit is a particle size of less than 150 microns.